The three-body problem is a problem in physics and classical mechanics that involves studying the motion of three-point masses under the influence of gravity. 1. It is a special case of the more general n-body problem, which deals with any number of masses. 1. The three-body problem is very difficult to solve analytically, because there is no general closed-form solution for the equations of motion. 1. This means that the positions and velocities of the three bodies at any given time cannot be expressed by a simple formula, but rather require numerical methods or special cases. 1. The three-body problem has many applications in astronomy, such as modeling the orbits of planets, moons, asteroids, comets, and stars. 1. One of the most famous examples of the three-body problem is the one involving the Earth, the Moon, and the Sun, which affects the tides, eclipses, and the stability of the Moon's orbit. 2. There are some special solutions to the three-body problem that have been discovered over the years, such as the Lagrange points, the Euler's collinear solution, the Pythagorean solution, and the figure-8 solution. 1. These solutions describe some specific configurations and motions of the three bodies that are stable or periodic. However, these solutions are rare and do not cover the general case of the three-body problem. 1. The three-body problem is also the title of a novel by Chinese science fiction author Liu Cixin, the first in the Remembrance of Earth's Past trilogy. 2. The novel explores the consequences of a secret project during the Cultural Revolution that attempts to contact an alien civilization in a nearby star system with three suns. 2. The novel won the Hugo Award for Best Novel in 2015, and was translated into English by Ken Liu. The three-body problem is a classical problem in physics and mathematics that asks how three masses, such as stars or planets, will move under their mutual gravitational attraction, given their initial positions and velocities. It is a very difficult problem to solve, because the equations of motion are nonlinear and chaotic, meaning that small changes in the initial conditions can lead to large differences in the final outcome. There is no general formula or algorithm that can predict the exact motion of the three bodies for any arbitrary initial conditions. 12. The three-body problem can be stated mathematically as follows: let and be the masses of the three bodies, and let and be their positions as functions of time. Then, according to Newton's law of universal gravitation, the forces acting on each body are given by F1 F2 F3 equals gr1 2 3 m1 m2 r1 r2 gr1 3 3 m1 m3 r1 r3 equals gr2 1 3 m2 m1 r2 r1 gr2 3 3 m2 m3 r2 r3 equals gr3 1 3 m3 m1 r3 r1 gr3 2 3 m3 m2 r3 r2. Where is the gravitational constant, and are the distances between the bodies? Using Newton's second law of motion, we can write the equations of motion as m1 dt2 d2 r1 m2 dt2 d2 r2 m3 dt2 d2 r3 equals f1 equals f2 equals f3. This is a system of 9 second-order ordinary differential equations, which can also be written as 18 first-order equations by introducing the velocities, and as new variables. The problem is to find the solutions, and that satisfy these equations, given some initial values for, and at some initial time. The three-body problem has been studied extensively since the time of Isaac Newton, who solved the simpler two-body problem and derived Kepler's laws of planetary motion. However, the three-body problem proved to be much more challenging and resisted all attempts to find a general solution. Some special cases and approximate solutions have been found, such as the circular restricted three-body problem, where one of the masses is negligible and the other two move in circular orbits around their common center of mass. In this case, there are 5 points, called Lagrange points, where the third body can remain stationary or move in periodic orbits. 34. The three-body problem is also important for understanding the dynamics and stability of many systems in astronomy, such as binary stars, planetary systems, asteroids, comets, and galaxies. It is also relevant for other fields of physics, such as atomic and molecular physics, where the interactions of three particles can lead to complex phenomena such as scattering, ionization, and chemical reactions. The three-body problem is also a source of mathematical beauty and mystery, as it exhibits rich and diverse behaviors, such as periodic, quasi-periodic, chaotic, and collisional orbits. The three-body problem can help us understand the formation and evolution of planetary systems, such as the Earth-Moon-Sun system, the Jupiter-Saturn-Uranus system, and the Pluto-Charon-Nix system. 12. The three-body problem can also help us study the dynamics and stability of binary stars, which are systems of two stars orbiting each other. Some binary stars can interact with a third star or a planet, leading to interesting phenomena such as mass transfer, orbital changes, and gravitational waves. 23. The three-body problem can also be relevant for nuclear physics and particle physics, where the interactions of three particles can result in complex processes such as scattering, ionization, and chemical reactions. For instance, the three-body problem can describe the decay of a proton into a neutron, an electron, and a neutrino too. These are just some examples of the real-world applications of the three-body problem. There are many more, and new ones are being discovered as we explore the physical world. The three-body problem is a fascinating and challenging problem that has inspired many scientists and mathematicians throughout history. Scientists solve the three-body problem by using various methods, depending on the context and the goal of the problem. Some of the methods are numerical methods. These are methods that use computers to simulate the motion of the three bodies step by step, using numerical algorithms and approximations. Numerical methods can provide accurate and detailed solutions for specific initial conditions and time intervals, but they are limited by computational resources and errors 1, 2, 3. Analytical methods. These are methods that use mathematical formulas and techniques to find exact or approximate solutions for some classes of the three-body problem. Analytical methods can provide general and elegant solutions for certain cases, such as the restricted three-body problem, the Lagrange points, and some periodic orbits. However, analytical methods are very difficult to apply and often fail to capture the full complexity and diversity of the three-body problem 1, 2, 4. Statistical methods. These are methods that use probabilistic and statistical tools to study the properties and behavior of the three-body problem in a large-scale or long-term perspective. Statistical methods can reveal some patterns and trends of the three-body problem, such as the distribution of orbital elements, the stability of orbits, and the occurrence of colisions and escapes. However, statistical methods cannot predict the exact outcome of a specific three-body problem 25. These are some of the main methods that scientists use to solve the three-body problem. Each method has its advantages and limitations, and none of them can provide a complete and universal solution for the three-body problem. Therefore, scientists often combine different methods and compare their results to gain a better understanding of the three-body problem. Scientists choose which method to use for solving the three-body problem based on several factors, such as the purpose and scope of the problem. Different methods have different strengths and limitations, and some may be more suitable for certain goals and contexts than others. For example, numerical methods can provide accurate and detailed solutions for specific initial conditions and time intervals, but they are limited by computational resources and errors. Analytical methods can provide general and elegant solutions for certain cases, such as the restricted three-body problem, the Lagrange points, and some periodic orbits. However, analytical methods are very difficult to apply and often fail to capture the full complexity and diversity of the three-body problem. Statistical methods can reveal some patterns and trends of the three-body problem, such as the distribution of orbital elements, the stability of orbits, and the occurrence of colisions and escapes. However, statistical methods cannot predict the exact outcome of a specific three-body problem 12. The availability and reliability of data and information. Different methods require different types of data and information, and some may be more accessible and trustworthy than others. For example, numerical methods need the initial positions and velocities of the three bodies, which may be measured by observations or experiments, or estimated by models or assumptions. Analytical methods need the masses and gravitational constants of the three bodies, which may be known or unknown, or vary with time or space. Statistical methods need a large number of samples or simulations of the three-body problem, which may be obtained by empirical or theoretical methods, or affected by biases or uncertainties 12. The level of complexity and difficulty of the problem. Different methods have different levels of complexity and difficulty, and some may be more feasible and efficient than others. For example, numerical methods are relatively simple and straightforward, but they can be very time-consuming and computationally intensive, especially for long-term or high-precision solutions. Analytical methods are relatively complex and sophisticated, but they can be very elegant and insightful, especially for special or general solutions. Statistical methods are relatively moderate and flexible, but they can be very approximate and probabilistic, especially for large-scale or long-term solutions 12. These are some of the main factors that scientists consider when choosing which method to use for solving the three-body problem. Of course, there may be other factors, such as personal preferences, professional backgrounds, or ethical implications, that may also influence the decision. Therefore, scientists often combine different methods and compare their results to gain a better understanding of the three-body problem. Scientists validate their solutions for the three-body problem by using various methods, such as comparing their solutions with observations and experiments. Scientists can test their solutions against real data from astronomical or physical systems that involve three bodies, such as planetary systems, binary stars, or atomic colisions. By comparing the predicted and observed motions, positions, velocities, and energies of the three bodies, scientists can check the accuracy and validity of their solutions. 12. Checking the consistency and stability of their solutions. Scientists can also verify their solutions by examining their mathematical and physical properties, such as conservation laws, symmetries, periodicities, and bifurcations. By checking if their solutions satisfy these criteria, scientists can ensure the consistency and stability of their solutions. 34. Evaluating the errors and uncertainties of their solutions. Scientists can also estimate the errors and uncertainties of their solutions, especially when they use numerical or approximate methods. By analyzing the sources and effects of errors and uncertainties, such as truncation errors, round-off errors, initial conditions, numerical algorithms, and models, scientists can assess the reliability and robustness of their solutions. 25. These are some of the main methods that scientists use to validate their solutions for the three-body problem. Each method has its advantages and limitations, and none of them can provide a perfect and universal validation for the three-body problem. Therefore, scientists often use multiple methods and compare their results to gain a better understanding of the three-body problem.